All right, mathematicians, let's get familiar with inscribed angles and inscribed polygons. Section 10.4. So our lesson objectives are to use these inscribed angles and polygons. And our essential question is, how are inscribed angles related to their intercepted arcs? Also, how are the angles of an inscribed quadrilateral related to each other? All right, so let's get familiar with some vocabulary. At the beginning, we have inscribed angle. It's an angle whose vertex is on a circle and whose sides contain chords of the circle. So here we have an example. The vertex of angle ABC, as you can see, is on the circle. So angle ABC is considered an inscribed angle. All right, the intercepted arc, an arc that lies between two lines, rays, or segments. So here we have arc AC. So we say that angle B intercepts arc AC. And then what it means to be subtend. If the endpoints of a chord are an arc, lie on the sides of an inscribed angle, then the chord or arc is said to subtend the angle. So what we're saying here is that arc AC subtends angle B. Segment AC, so if I were to connect A and C to create a segment, we say that segment AC subtends angle B. All right, so here's our first theorem of this new section. It's the measure of an inscribed angle theorem. So essentially, the measure of an inscribed angle is 1/2 the measure of its intercepted arc. So we can say that angle ADB, its measure is half of the intercepted arc's measure, and our arc is AB. So our implied is measure of inscribed angle implies half the measure of intercepted arc. All right, so we can look at this relationship in one of two ways. First, let's take a look at this left image where we have the inscribed angle labeled x and our intercepted arc is labeled 2 times x. And that's the relationship. Whatever your inscribed angle is, the intercepted arc measure is twice the measure of the inscribed angle. Or you could look at it in this way. Whatever the intercepted arc measure is, the inscribed angle is half. In other words, divide by 2. So let's take a look at our example 1, where we can use our inscribed angles to figure out either arc measures or inscribed angle measures. So the measure of angle T, I'm going to find that out, which is right here. And it looks like its intercepted arc is RS, which has a measure of 48 degrees. So that means if we take half of 48, we will get the measure of our inscribed angle, which is 24 degrees. Now let's take a look at the measure of arc QT. Now the measure of arc QT is the intercepted arc. QT is the intercepted arc of inscribed angle R, which is measuring at 50 degrees. So if we double that, we get a measure of 100 degrees. All right, let's take a look at example 2, finding the measure of an intercepted arc. So let's find the measure of arc RS and the measure of angle STR. And then what do you notice about the angles STR and RUS? So we can see that we're given an inscribed angle 31 degrees. So we can conclude that the intercepted arc, so arc RS, is going to be double that, so 62 degrees. And if RS is 62 degrees, then its intercepted arc over here goes with angle, the inscribed angle T. So that means if we take half of 62, then we get 31 degrees here. So here's all the information. And so what do we notice about these two angles? These two angles are congruent. This leads us into our next theorem, the inscribed angles of a circle theorem. So if two inscribed angles of a circle intercept the same arc, then the angles are congruent. Pretty straightforward. So let's see if this works for our example number 3, finding the measure of an angle. For given the measure of angle E is 75 degrees, which is already labeled in our picture, then find the measure of angle F. Well, here's what we need to notice. Angle E's angles, the ends of the angles, if you trace it, hits at G and H. So the intercepted arc is GH for angle E. Let's follow angle F's sides going to G and H. So that means these two inscribed angles intercept the same arc GH. So what can we conclude about angle F? It's equal to angle E, therefore 75 degrees. All right, let's now move on to our inscribed polygons, which are polygons in which all vertices lie on a circle. So just like our inscribed angle, the vertex was on the circle, that's true for our polygons that are inscribed as well. All vertices, however many there are on the circle. So we can see here is a great example of an inscribed polygon. It's a pentagon, and so all vertices are on the circle. Here we have inscribed right triangle and an inscribed quadrilateral. Now, circumscribed circle, it's a circle that contains the vertices. So this red outlined circle is considered circumscribed about the polygon. We have circle D and circle C, also circumscribed circles. All right, so this leads us into two different theorems dealing with inscribed polygons. So let's take a look at the first one, which is our right triangle inscribed theorem. So if a right triangle is inscribed in a circle, then the hypotenuse is a diameter of the circle. Conversely, if one side of an inscribed triangle is a diameter of the circle, then the triangle is a right triangle, and the angle opposite the diameter is the right angle. Here in this example, we can say that measure of angle ABC is 90 degrees if and only if segment AC is a diameter of the circle. So our implied right triangle inscribed in triangle implies hypotenuse is diameter. And then our other inscribed polygon theorem, the inscribed quadrilateral theorem, states that a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So here in this example, vertices D, E, F, and G lie on circle C if and only if the measure of angle D plus measure of angle F, so D plus F, opposite angles, is equal to the measure of angle E plus measure of angle G, also opposite angles, which is equal to 180 degrees. So we have an inscribed quadrilateral in a triangle if and only if opposite angles are supplementary. All right, let's see if we can use our two inscribed polygon theorems to find the value of each variable in example 4a and example 4b. All right, so our theorem states for a triangle, inscribed triangle, that if one side of an inscribed triangle is a diameter of the circle, then the triangle is a right triangle, and the angle opposite the diameter is our right angle. So here we can see that segment AB is passing through the center at Q. So that means this must be our diameter. So we can conclude that this is a right angle. So we can set up an equation. 2x equals 90 degrees divided by 2, so x equals 45. All right, let's take a look at our second example where we have a quadrilateral inscribed. And we know that our theorem states that a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So that means we can set up two separate equations. The first one, we can say the measure of angle D plus the measure of angle F equals 180 degrees because they are opposite angles. Substitute Z and 80. So Z plus 80 equals 180. Subtract 80 from both sides, so Z equals 100. We can set up our other equation with our remaining opposite angles, E and G, that must add up to be 180. Substitute 120 for E and Y for measure of angle G. So 120 plus Y equals 180. Subtract 120 from both sides, so Y equals 60. All right, here's our next construction in Unit 10. Let's construct a square inscribed in a circle. So given circle C, construct a square inscribed in a circle. So go ahead and sketch your circle. Doesn't matter the radius, but I gave you some space in your notes. So sketch out a circle using your compass. First step, draw in the diameter and label the endpoints A and B. Step 2, construct a perpendicular bisector of your diameter AD. Label the points where it intersects circle C as points D and E. And then finally, connect points A, D, B, and E to form your square. All right, let's take a look at a real-world application using a circumscribed circle. So pause the video here to read your word problem. All right, let's consider a half of the circle here. So sketching in a semicircle that includes the original right triangle inscribed on a semicircle. So we don't need the full circle to go all the way around, since we only want the front view of this Lady Liberty statue. So that means we could just sort of move our right angle, inscribed angle, to a couple of different locations along that semicircle. Since all of these inscribed right angles have the same diameter, and remember, if a right triangle is inscribed in a circle, then the hypotenuse is the diameter of the circle. So our diameter is along the base edge of our statue. And our statue will fit perfectly within our camera's 90-degree field of vision from any of these points. Alright, so go ahead and pause the video here and try these two examples on your own, and then unpause to check your answers. Alright, so check your answers. X equals 98, Y equals 112 for part A, and X equals 10, Y equals 62 for part B. Come in with any clarifying questions tomorrow when I see you in class. And I stumbled upon this. Yes, ladies and gentlemen, that's a real purse made out of a hula hoop. Who knew? Have a good evening.